In this video, we'll be working on the first lesson of this new unit of polynomial functions. So let's first start off by talking something that you're pretty familiar with, which is a polynomial expression. I know what we have here on the piece of paper might be a little complicated, but this is something that you're actually pretty good at because you worked a lot on it in grade 9, 10, and 11. So I'll write something that you're more familiar with. So what this is really saying is you have a collection of terms which you're adding or subtracting, but something like this, 3x squared minus 5x plus 6. That is an expression that you should be very comfortable with because you've seen this many times in grade 10, for example. So whenever you have a polynomial expression, you can talk about a few details about it. You can say, what's the degree of this expression? So hopefully when you look at 3x squared minus 5x plus 6, we can all agree that the degree of this expression is 2 because the greatest power of x is 2. So we have an x squared term, we have x to the power of 1, and we have a constant term. So hopefully you can see that 2 is the greatest power of x. So we say that the degree of this term is 2. Now later on in this unit, we're going to work with degrees of, I don't know, could be 5, 6, 7, 8, 9, 10. So we're no longer going to cap ourselves at a degree of 2. So for example, if I have another expression here, 50 or 5x to the power of 10 minus 9x squared plus 7x to the 11, hopefully you can say that this expression has a degree of 11. Okay, so what else do we want to talk about? We want to talk about coefficients. Okay, so whenever you have an expression, a polynomial expression, we also want to talk about coefficients. So what is a coefficient? In grade 9, you might have also called it a numerical coefficient. So the coefficient of a term is the real number that's associated with that term. So for example, we have 3x squared here. So 3 times x squared, which makes 3 our numerical coefficient. Now, more specifically, we also have this thing called the leading coefficient. And that's very important because later on you'll realize that the leading coefficient actually tells you a lot about the polynomial. Okay, so the leading coefficient is the coefficient which is associated with the leading term. And what is the leading term? The leading term is a term that has the greatest power of x. So for example, 3 is the leading coefficient. And 7 is our leading coefficient here. Okay, and of course we also have a constant term. A constant term does not have a variable associated with it. Okay, so these are polynomial expressions, and of course later on we're going to talk about polynomial functions. So how do you go from expression to polynomial function? You just have f of x equals that polynomial expression. As a side note, when we write polynomial functions or polynomial expressions, we write it in standard form, which means descending order of power. So if we have an x cubed term, an x squared term, and a constant term, you write the x cubed term first, and then the x squared term, and then the constant term. Any other way would be rather silly. Okay, so in this course, we're going to be working with lots and lots of different functions. So we'll just first start off by identifying what a polynomial function is because we don't want to get it confused with the other functions we'll be working with later on in this course. So which of these are polynomial functions? And if it is a polynomial function, we want to establish what the degree is and what the leading coefficient is. Okay, so f of x equals 3x cubed minus 5x squared plus 2. Hopefully we can agree that that is a polynomial function. So if it is, then we're going to say the degree, the greatest power of x is 3. Okay, the leading coefficient, so what is the coefficient associated with the leading term? So it's also 3. Okay. All right, let's do g of x here. Is that a polynomial function? Yes, absolutely. So degree, hopefully you didn't get tricked. So I didn't write this polynomial function in standard form. So hopefully you can say that the degree of this polynomial function is 5. And because this is the leading term, then that means our leading coefficient is -7. Okay. Later on in the course, we'll be working with h of x. So h of x is not a polynomial function. So hopefully you can realize that this is not only would you say that's not a polynomial function, but hopefully you're going to identify that this is a trigonometric function, which is something you studied in grade 11, and we're going to study again in advanced functions. Okay, what about I of x? Once again, that is not a polynomial function. Hopefully you recognize that this is an exponential function. Okay, awesome. So like I said, we're working on polynomial functions. Now for the first lesson, what we're going to do is we're going to study a specific type polynomial function, okay? And by doing so, it's going to help us learn about polynomial functions in general, okay? So the type of polynomial functions we're going to learn about is called a power function. So what is a power function? It's a specific type of polynomial function. So I have a little quick definition here. A power function is the simplest type of polynomial function. Essentially, you can think of it as a one-term polynomial or a single-term polynomial. So a times x to the power of n. Okay, so x is of course our variable, n is a whole number, and a is a real number. Now, I'll say it one more time. If we become very good with working with power functions, then that would be very helpful down the road when we study more complicated polynomial functions. Okay. And I also talked about degrees. So we could say a degree 1 polynomial, but we usually call it a linear function. If it's degree 2, we say it's quadratic, 3 is cubic, 4 is quartic, and 5 is quintic. So if I say quartic, I hope you remember that's a degree of 4. Okay, so let's keep adding some definitions here. So we have power functions, and we're going to break it down to 2 groups, okay? We have power functions which have an odd degree, okay? And we have power functions which are even degree. Now it's pretty self-explanatory. So 3x to the power of 5, that is an odd degree power function because the degree is 5 and 5 is an odd number. And then we have f of x equals 4x squared, and this is of course an even degree power function. It's a one-term polynomial, and its degree is 2, which makes it even. Okay, so what we're going to do is we're going to look at the graphs of some even degree power functions and odd degree power functions. Okay, and then take your time, and we're going to study the properties of the graph. Okay, so I have 6 even degree power functions here. Okay, and then I have 6 odd degree power functions here. So take your time, look at the graphs, and try your best to fill in this or these 2 tables. Okay, so you can pause the video, try to do it yourself. Some of them will be a little tricky for you, but take your time. Okay, so hopefully you're done. Let's do domain. Okay, actually before we fill in the table, I want to show you that hopefully you realize there's a pattern. So yes, these 6 functions are all even degree power functions, but hopefully you realize that the leading coefficient for these 3 are positive, and leading coefficient for these 3 are negative. Okay, so the first row, even degree power functions with positive leading coefficient, and this is even degree power functions with negative leading coefficient, and same here, odd degree power function, positive leading coefficient, and then odd degree power function, negative leading coefficient. Okay, so we really have 4 things to look at. Okay, so the easiest thing we want to talk about is the domain. Okay, the domain of polynomials is actually very straightforward. Whether you study a power function or not, actually, it's always going to be all real numbers. And in fact, I would argue that because the domain of polynomial functions is always all real numbers, it's one of the reasons why we start off by studying polynomial functions first, as opposed to an exponential function. Even though, let's say, I don't want to spoil it, but because the domain is all real numbers, it makes it easier to work with. So we start studying polynomial functions instead of, let's say, a rational function, which we'll get to down the road. All right, so let's talk about range. So hopefully by looking at the graph of the even degree power functions and the odd degree power functions, you can tell the range. Okay, so if this is odd degree, the range is all real numbers. Okay, now if it's even degree with a pos leading coefficient, then hopefully you'll notice that it's always y is greater than or equal to 0. And if it's odd degree with a negative leading coefficient, the range is all real numbers. And it's less than or equal to 0. Okay, so hopefully domain and range is pretty straightforward. Okay, so what might be troubling you is the symmetry and the end behavior. Okay, so we'll talk about the symmetry that you're pretty comfortable with, which is even degree power functions. So if you look at the even degree power functions, they do resemble parabolas, okay, which is something you studied in grade 10. So if you look at parabolas, they always have, if you think about the one that hasn't been transformed, parabolas always have this sort of symmetry, okay, which you can see with all these even degree power functions. Hopefully you can see that all these even degree power functions, they all have line symmetry. Okay, you can draw a vertical line and that splits your function into two symmetrical halves. So we're going to say line symmetry. But that's not good enough. Not only is it line symmetry, it's line symmetry with respect to y-axis, or about the y-axis. Okay, line symmetry with respect to y-axis. Okay, because you can have line symmetry anywhere. Okay, but it's very specific. If you look at the 6th graph, you have line symmetry with respect to the y-axis. Okay, we're always using the y-axis to split our graph into two symmetrical halves. Okay, now the next one, for odd degree functions or odd degree power functions, the symmetry is not as obvious. It's not something you've seen before. So I'll use this f of x equals 2x cubed. Okay, you could use any of the other 5, but what I'm going to do is I'm going to point on the origin, and then I'm going to rotate it, the piece of paper, upside down. Okay, hopefully you notice something nice. Okay, hopefully you notice that the graph is identical. Okay, as if I did not rotate the piece of paper. Okay, so you could do that to the other graphs, other odd degree power functions. You'll notice that it's exactly the same. After you perform a 180 degree rotation, it's exactly the same. So that kind of symmetry has two names. You can call it point symmetry because you're rotating the piece of paper about a point, or you can say it's rotational symmetry. But I'm going to use point symmetry. Okay, symmetry. But specifically, you're going to say point symmetry about origin. Okay, because I had to poke my pencil right at the origin. Otherwise, I won't get the beautiful, the graph to be the same. Point symmetry about origin. Okay, beautiful. Let's keep going. End behavior. So this is something we're going to talk about throughout the course. End behavior. And the key word here is end, okay? What do they mean by end? So when you see a graph, when we take a look at a graph, you want to go to the very, very, very far left and very, very far right of the graph. Okay, so you can even add arrows here. And you can imagine what happens to this graph if we extend it. We go to the very far left and the very far right. This polynomial is going towards infinity. Okay, as I go left, it's going up, and as I go right, it's going up. So don't think about what's happening in the middle of this graph. What's happening when x is equal to 0? We don't care. Okay, when x equals 1, we don't care. We care when x is a very, very large value. Okay, so there's a few ways to write end behavior. So I'm going to write it using a more technical way, and then we'll show you the shortcut. So for end behavior, you can say as x approaches. So far right and far left. So there's always going to be two lines. As x approaches infinity. So what this is saying is what's happening as I go to the far right of the graph, okay? Because x is approaching infinity, that means I'm going right. And you're going to say f of x, or you can say y is approaching. So be careful. This is an odd degree power function with a positive leading coefficient. So we're going to look at something like this graph, or this graph, or this graph. And you'll see as you go right, they're all doing the same thing. They're all going up. So f of x approaches infinity. And of course, you gotta go the other way. As x approaches negative infinity, f of x approaches. So what happens when I go left? So we can go back to the graph and see what happens when you go left. When you go left, because x is approaching negative infinity, it's going down. The graph is going down. Okay? So the shortcut is looking at the graph. Okay, so I'll go back to a positive leading coefficient and odd degree power function. We look at the graph and hopefully remember the labeling of the quadrants. Quadrant 1, 2, 3, and 4. Okay, when you're working with polynomials, you'll start in one quadrant and you'll end up at another quadrant. Okay, so for odd degree power functions with a positive leading coefficient, okay, if we look at the end behavior, this function extends through, it starts off from quadrant 3, and then it goes to quadrant 1. 3 to 1. 3 to 1. Okay, so we say quadrant 3 to quadrant 1. Okay, so be careful with both ways, okay, with both notation, because on the test you might be given this, and I don't want you to be confused. I don't want you to be always relying on quadrant 3 to quadrant 1. Okay, so the key idea though is end behavior means what happens when you go to the far left of the graph and the far right of the graph. Or you can think of it as algebraically, what happens to your function as x approaches infinity, and what happens when x approaches negative infinity. Okay, so let's do even degree power functions with positive leading coefficient. So hopefully you can look at the graph. That's going to be quadrant 2 to quadrant 1. Now if it's a odd degree power function with a negative leading coefficient, it's quadrant 2 to quadrant 4. And lastly, even degree power function with negative leading coefficient will be quadrant 3 to quadrant 4. Okay, so the last thing I would want any student to do is to memorize this table. Please don't memorize the table. But saying that, I do need you to know about the symmetry. I need you to know about the end behavior of power functions with different leading coefficients. So to help you with this, okay, if you're struggling to remember anything, please don't memorize it. All you have to do is just think of the 4 basic functions. Okay, I'll write it at the bottom here. All you have to do is think about grade 9 and grade 10. The simplest power functions, you already know them. You already work with them. So you just think of y equals x, y equals minus x, y equals x squared, y equals minus x squared. And I really hope you would know how these graphs look like. So y equals x, that goes to origin, y equals minus x, y equals x squared, and minus x squared. So you should know the end behavior based on what you learned previously. Okay, so if you ever forget what's the end behavior of odd degree power function with a negative leading coefficient, just draw y equals minus x, or imagine that in your head, and then you will see all the properties that you want to see. For example, you should see point symmetry about the origin. You should see it extends from quadrant 2 to 4. Okay, so please don't memorize the table. So like I said, we are going to work with polynomials of any degree. So we have 8 functions here. Which of these have the following end behavior and the reasons? So quadrant 3 to 1, let's see. Y equals 2x, y equals x to the 7. How do I know that? Because leading coefficient is positive, and we have odd degree. Okay, there's no other function that has a leading coefficient which is positive and an odd degree. So if it's 2 to 4, okay, if it's 2 to 4, I'm looking for functions with a negative leading coefficient and an odd degree as well. So let's see. Negative 2 to 5 x to the power of 9. What else? Negative. I'm going to rewrite it. Negative 1/4 x to the power of 1035. Okay, a lot of students get confused when it's written like this. That's just a leading coefficient of negative 1/4. So leading coefficient is negative odd degree. That's the only way I'm going to get this end behavior. Okay, quadrant 2 to 1, that means I'm looking for even degree and positive leading coefficient. Even degree. And last one, quadrant 3 to 4, so negative leading coefficient and even degree. I'll rewrite this one as well for you. Okay, so this first lesson is just to introduce some terminology about polynomial functions and specifically focusing on power functions, which is a single term polynomial, and that would really, like the knowledge you have with respect to power functions was really going to help us study the other polynomials. Okay, hopefully that wasn't too bad.